All right. Okay, so in terms of retrosynthetic analysis, all it means is that we do the reaction sequence in reverse order, right? So we start with the last first, and this is a strategy that we've employed many times throughout this semester, and we've even done it today. You want to ask yourself questions like, is the carbon skeleton changing, right? Same old questions we always ask. Is there a change in the functional group position or the type of functional group? And so I think the best thing to do is to ask yourself, what kind of functional groups are you dealing with? If you take a look at this synthesis here, we're going from this primary alcohol to a terminal alkyne. Now, a primary alcohol isn't a good leaving group for one thing, so we'd have to convert that into a leaving group. So you might look at this and say, well, how would I go from an alcohol to an alkyne? So if you were to get stuck on a problem like this, what I think the best thing to do would be to take a step backwards, right? And think about it in terms of retrosynthesis and say, well, really the only option that I have would be to have this compound at some point, because I know that I need to have that vicinal dibromide in order to do the double elimination followed by addition of water, right? So that takes you back a step. And that means you've got a couple of steps in the synthesis complete already. But then the question is, well, how am I going to get from the primary alcohol to here? Right. So in that case, it might be good to do a double retrosynthetic analysis. So we think about that first step, okay? And we say, well, we know that we could make a vicinal dihalide like that from an alkene, right? So we've kind of figured out the last step already. So we've got this step done. Then if I think, okay, well, how am I going to make this vicinal dibromide? Again, the only way that we know how to do that would be to start with this alkene, right? So then the question becomes even more simplified, right? We have to get from here to here. We're basically going backwards step by step. And so there's the alkene that we need. We know that we can just treat that with bromine in a solvent like carbon tetrachloride to do the bromination reaction. And now we've again rendered the question even simpler, because now we just need to convert that primary alcohol to an alkene. Well, I know that I can convert the primary alcohol to a good leaving group using tolusyl chloride and pyridine. And then all I have to do is an elimination. And since it's going to be a primary leaving group, I would want to use a strong base, weak nucleophile. So let's take a look here. And so what would we do overall is that you take this, you treat it with tolusyl chloride and pyridine, then you treat it with a strong base that's a terrible nucleophile like DBU or DBN to do the elimination to produce the Hoffman alkene. Then you do the double elimination followed by addition of water after the bromination, of course, to produce the alkyne. So I think this is a really great example of how it might be handy to go backwards, right? Just to solve it using retrosynthetic analysis. So overall, it's a 5-step synthesis, right? Treating it with tolusyl chloride to create a good leaving group. Then again, it says potassium t-butoxide here. You could use DBU or DBN. Either one's going to work. You just need a strong strong base that's a weak nucleophile. Then you have the bromination to make the vicinal dibromide. Then you treat it with excess sodium amide to do the double elimination. You produce the alkanide. Then you add water in the last step to add this proton on the end like that. And there you have it. But again, I think the most powerful way to solve this problem would be to use retrosynthetic analysis. So that's retrosynthetic analysis. So with all that in mind, let's try some more problems here. This is question 11.9, and we're just asked to propose an efficient synthesis. It's not asking us to propose any kind of retrosynthesis. And so I recommend if you can do the reaction, or if you can solve the problem just by going forward, there's nothing wrong with that at all. But if you want to do it in terms of retrosynthesis, it could be handy. So let's take a look here. I'm going to need a blank document here. So let's see. Let's find some room down here. So this is question 11.9, right out of your textbook. Question 11.9, and we're going to start with A. So we start with acetylene, and we want to convert that to this alcohol, which has a primary bromide in it as well. So The last step is going to have to be halohydrin formation, isn't it? Because we have a hydroxyl and a bromine. Now, if you know where to start right away, you can do that, but it might be wise to think about this using retrosynthesis and say, well, if I had 1-butene, all I have to do is treat that with bromine in water, and that's going to do or form the halohydrin, isn't it? And so then the question is a lot simpler, just going from acetylene to 1-butene, because we know that all we would have to do is add 2 carbons to our acetylene. So first we would treat it with sodium amide, followed by ethyl iodide or ethyl bromide. We'll use that this time. And that would give us 1-butyne. And we know we can convert 1-butyne into 1-butene a couple of ways. We could either use hydrogenation and Lindlar's catalyst, or we could use sodium metal reduction. I'll choose hydrogenation and Lindlar's poisoned catalyst. Okay, that works really well. And then for the last step, all I have to do is treat it with bromine in water, and I form my halohydrin. So halohydrin formation. Okay, the next one that I had on that slide is question E. So you're starting with this compound, son of a gun. So this is 2,3-dimethylbutane. I just find it hard to draw on the bottom of the iPad. And we want to make it into a primary alcohol. I want to make this compound where we have the alcohol over here. Well, since this section we're dealing with retrosynthetic analysis, what would be the obvious thing to do here retrosynthetically would be to have this alkene and then just to do an anti-Markovnikov addition of water, right? Anti-Markovnikov addition of water using borane and THF followed by hydrogen peroxide and sodium hydroxide. So then the question becomes, well, how do I get from here to here? Well, the good news is that with this starting material, you literally have only one reaction you could use. Could anybody tell me what that reaction would be? Only one useful reaction, I should say. You could burn it, but that's not very useful. Just making a bunch of carbon dioxide and water wouldn't be super helpful. Could anybody suggest what would be a useful reaction here? So, yeah, we'd want to do a bromination reaction, right? We want to treat it with bromine and light. Yes, or heat. Exactly. And that would make this compound where we have now the tertiary alkyl halide. Remember, whenever you have an alkane as a starting material, you could do a combustion reaction, but that's just burning it. So bromination is going to be your best bet. So now you've functionalized it. And there are 2 beta protons, aren't there? If we examine this alkyl halide, this is the alpha carbon, but then we have a beta carbon over here, and we have a beta carbon over here. So we have 2 types of beta protons, right? We have these ones in blue. If you eliminate that one, you'll produce the Hoffman alkene. If you were to eliminate this one in green, then you'd produce the Zaitsev alkene. Well, obviously, we want to eliminate the one in blue. And so for that, we would use a hindered base. So we would use something like potassium T-butoxide, which is a hindered base, and that would give us, the desired alkene. Get our double bond here. And then the last 2 steps are going to be anti-Markovnikov addition of water. So we treat it with borane and THF, the first step, followed by hydrogen peroxide and sodium hydroxide in the next step. And there you have it. There. I think this is another great example of using retrosynthesis. And let's take a look at H. So this is 11.9H. Just move up here. So 11.9H. And the question looks like this. We start with this molecule, which is 2-methylbutane. And we want to convert it into this compound, which is 3-methyl-1-butyne. And so, you're starting with an alkane. If you like to go for the low-hanging fruit, which I do, okay, if all you've got is one option, you could just start with that and say, well, I'll see what happens after I do the first step. See what my brain thinks, okay? So there you go. You added a bromine. But if you're still like, I'm not sure what to do next, let's look at it in terms of retrosynthesis. Let's back up and say, okay, well, to make that triple bond, we know we would have to have the vicinal dibromide. In order to have the vicinal dibromide, the only way I know how to do that is to have this alkene. Now the question becomes much more manageable. I want to get from here to here somehow. Okay, I want to have that Hoffman alkene. Well, if I look at this alkyl bromide, I've got this type of proton in blue, and I've got this kind of proton in red. So if I want to pull off the proton in red, I would use sodium ethoxide or sodium methoxide because it is the more hindered proton, but it's going to produce the Zaitsev alkene. So let's try that. We'll hit it with sodium. Let's try methoxide just to be fun. Okay, and what are we going to have? We're going to end up with this compound where we have the double bond here. Well, now we need to go from here to here. Okay, well, if we did an anti-Markov-Nikov addition of HBr across that double bond, then we would have the bromine in the right spot, right, in order to do another elimination, right, because you've got beta protons, or beta proton here, and you've got beta protons here. To pull off that one in red, you'd use potassium T-butoxide, right? You'd use a hindered base. Okay, so let's do that. I'm going to run out of space here, aren't I? Anyhow, you know what? Let's do it like this. Let's say we're going to treat this with potassium T-butoxide. Okay, like that. And that's going to give us this compound. Okay, and then for the last two steps, we'll kind of mix it all together here. The first step is going to be bromination. That's going to yield this compound. Then you're going to treat it with excess sodium amide. And then you're going to treat it with water. And that's going to make the triple bond. So look at that. That's quite a few steps, isn't it? We've got a total of 1, 2, 3, 4, 5, 6, 7. 7-step synthesis. That's nothing to sneer at, my friend. Okay, that's not a joke. That's a lot of steps of 7 steps. And, you know, going forward, if you are able to solve these problems just by looking forward and saying, yeah, I can figure that out. Okay, nothing wrong with that whatsoever. But if you ever get stuck, and I think that, you know, most scientists get stuck at some point in their lives, you know, in that case, it's probably wise to think about it in terms of a retrosynthesis like this. Make it into something that might be a little bit easier for you. You know, I do it all the time. Okay. There's a story about a famous researcher who was doing total synthesis, meaning making new molecules or synthesizing molecules that had never been synthesized before. So natural products, meaning compounds that are isolated from natural resources like plants. And what he would do is when he was thinking about developing a new synthesis, he would write the structure of a complex molecule on the corner of a chalkboard in his office, and he'd leave it there for 1 year, and he would look at it for the whole year. Meaning, I don't mean he'd look at it for 8 hours a day, but he'd have it up there, so it would always be in his mind's eye. And then he would just think about all kinds of different retrosyntheses, or let's say somebody walked into his office, he might engage them in a conversation about it. And so, you know, retrosynthesis is really powerful. And in fact, I think that retrosynthesis was developed by E.J. Corey. So Elias Corey, I think, is still alive. Anyhow, so E.J. Corey, who is arguably one of the most famous organic chemists on the planet Earth. He's at Harvard University. He won the Nobel Prize. But yeah, he's definitely one of the most famous organic chemists on the planet Earth. Okay, he's right there up at the top, I'd say. Maybe the most famous organic chemist on Earth. Not the most famous in history. The most famous in history is R.B. Woodward. R.B. Woodward. And I had a professor when I was in graduate school who used to say, nobody knows everything, you know, but in fact, that's not exactly true, because he said Woodward did know everything. I don't know if that's true, but now he used to say this guy knew everything. Anyhow, let's move on. Now, it says here to skip the section on green chemistry, but I want to talk to you about it briefly. And it might be worth the value of one multiple choice question if you're like, well, why do you have the word skip on it? Because I used to skip it, but, you know, this being 2021, okay, we're in 2021 now. I think that we would be remiss to just totally skip over this. And let me explain what I mean, because green chemistry refers to reactions that are more environmentally friendly, right? Everybody wants to do chemistry now that is environmentally friendly. I mean, think about it. If you could do a reaction, which is fine, but causes pollution to our planet versus a reaction that does the exact same thing and the exact same yield that doesn't cause pollution, well, sign me up. I'm ready to do the reactions that don't cause pollution. Let's face it, chemistry does cause a lot of waste. And so when we can avoid waste, that's always going to be a good thing, right? That's not just a good thing for a chemist. That's a good thing for anybody on the planet, as far as I'm concerned. So we want to try to prevent waste as much as possible. We want to use less hazardous substances, right? If you could do a Markovnikov addition using just aqueous acid versus using oxymercuration, demercuration, well, you are going to avoid using oxymercuration, demercuration when you can, because it involves mercury, right? Which is a metal, which is a, dangerous heavy metal. And we could get into that, why it is, but anyhow, also solvents, right? We want to use safer solvents. I mean, back in the olden days, in the 60s and the 70s, chemists used to literally wash their hands with carbon tetrachloride, okay? Carbon tetrachloride. They would literally take it and wash their hands, and, I don't know what the word is, scrub. They would scrub their hands, which is frotter in French, but anyhow, they would scrub their hands with carbon tetrachloride. I want to tell you right now, you guys, if you go into a lab and you're like, I'm going to need some carbon tetrachloride, people start getting, whoa, 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 what are you doing? Are you sure you have to have it? It's actually, you can buy it for sure, but it's not easy to get as it used to be because people are trying to get away from it. And the last thing was developed by Barry Sharpless? No, Barry Trost. Yeah. So this was developed by Barry Trost, who again I think is still alive. I saw him give a presentation, but that was 20 years ago. I've actually seen him twice, Barry Trost. But anyhow, Barry Trost developed the concept of what's called atom economy, and that is simply using reactions where all or most of the atoms from the reagents are put into the products. Let me show you what I mean. If you take a look at these two ways to make an alcohol, right? And this is what I just referred to, right? We could either use oxymercuration, demercuration. It's a great reaction, but it's got a poor atom economy. If you think about all the reagents, the only thing from the reagents that ends up in the product is this little hydroxyl and this proton. That's it. Whereas in everything else, everything that's in red, where does that go? Down the drain. Okay, that is waste, my friend. Whereas if you just use a catalytic amount of acid and water, that's got great atom economy, right? The whole dang water molecule is being incorporated into the molecule. And if you're only using a catalytic amount, there's very, very little waste here. So that's a good example of atom economy. And this is a very poor example of atom economy. And if you're like, well, I'm going to never use that reaction again. Well, sometimes we're kind of caught between a rock and a hard place as chemists. And maybe it's a situation where we kind of have to be like, okay, I guess I got to do it. But we want to try to minimize waste whenever we can. Another example, think about the syn dihydroxylation that we looked at this semester. Right? I showed you conditions where you could use a stoichiometric amount of osmium tetroxide and sodium sulfite or sodium bisulfite, but I also showed you conditions where you could use a catalytic amount. Right? That just means a little tiny bit, and it gets regenerated by NMO, which is the co-oxidant, which basically regenerates the osmium tetroxide. So that's why people love these kinds of reaction conditions. They're safer for the chemist and they're better for the environment. Energy efficiency, it's one that I don't think about nearly as much. But, if you think about it, let's say you have a reaction and it takes, 5 hours at 100 degrees Celsius. Well, that means you've actually got to turn up the heat, don't you? You're not wasting, but you're using electricity. What if you could do the same reaction at room temperature? Well, you would maybe think about using that because you would save electricity. It's more energy efficient. And then the whole thing about renewable feedstocks, this is also a big thing. It was never a part of my life because I worked in pharma. I didn't think about, using grains and, just using ethanol for everything. But it is an idea for, I would say, more for large scale reactions where we try to use renewable resources like corn, grain, instead of, and everything else which comes from the petroleum industry, because petroleum is not a renewable energy source. It's not a renewable resource. Anyhow, so something kind of interesting there. I would say don't skip this. This might be worth the value of maybe one multiple choice question, and it would be something very, simple and hopefully obvious to you that this has got good atom economy. This is poor. But anyhow, again, if you're the kind of person who's really interested in chemistry, and what a chemist doing nowadays in 2021, I'd say if you want to get grant money, if you're a researcher, I mean, can't say this with exact certainty, but I think that green chemistry is a pretty hot area of research. And you can always pique somebody's interest when you say, "Oh, you have a way of doing that reaction. Well, I have a way of doing it that's much better for the environment." You're always going to make friends. At least I think you would. All right. And then in terms of increasing your proficiency, I mean, I could ask any one of you who's listening to this video or who's in class right now. I could say, I want you to write this section, and you could all do it. Okay. You could all write this section, probably really quickly and say, well, here's how I do it. Right. Everybody's got their own ways of, mastering synthesis, but I recommend, just practicing your reactions and practicing over and over and over. Okay. And just keep repeating them until they're kind of stuck in your mind. Okay. And something that you could do, I don't force my students to do this in any way, but something you could do is make your own synthesis problem. Start with something that's really simple, do a little reaction to it, and then just keep doing reactions to it. And then you take out all the reagents and then you give it to a friend and just say, hey, could you solve this problem? And there's an example here, let's say you started with acetylene, then you alkylate it, then you alkylate it again, then you reduce it, and then you say, okay, well, you give that to a friend and say, could you solve this problem? Or maybe you just hide it from yourself overnight and try to solve it in the morning and see if you could do that. Anyhow, kind of interesting there. Also, something that you've heard me say several times this semester is that oftentimes we have more than one way of solving a synthesis problem. Say, for example, you wanted to do an anti-Markovnikov addition of water across this double bond. I think that most commonly we use hydroboration oxidation, but you could think about doing this strategy where you would end up with a primary alkyl bromide and then just displace that with sodium hydroxide. That would totally work in this case. But later on, especially in organic chemistry too, and this is in the future, something you want to think about is that we always try to find the most facile synthesis, right? We want to find the easiest way of doing a synthesis. So what I'm saying is this: if you propose a synthesis that's 3 steps and somebody else proposes one that's 4 steps, I say they're probably both great. But if you have a synthesis that's 4 steps and somebody else does the same thing in 13 steps, well, I'm not going to say the 13 steps are necessarily wrong, but when I grade quizzes, paper quizzes, I wouldn't give that full credit, if there's something that could be done very quickly and then we're taking a long, kind of a long way around it, we try to avoid doing that at all costs. Anyhow, and there you have it. That brings you to the last slide of the last chapter of Organic Chemistry 1.